Neuromorphic computing, a term that sounds like it belongs in the realm of science fiction, is actually a cutting-edge field at the intersection of neuroscience and artificial intelligence. Imagine a world where computers not only think like humans but also mimic the very structure and function of our brains. That's the essence of neuromorphic computing. At its core, neuromorphic computing seeks to develop computer systems that replicate the brain's neural architecture, utilizing artificial neurons and synapses to process information in a manner that closely resembles how our brains do. This approach is in stark contrast to conventional digital computing, which relies on binary operations, while the human brain processes information through complex interconnected networks of neurons, allowing it to perform tasks like learning, recognizing patterns, and making decisions with remarkable efficiency. Neuromorphic computing holds tremendous promise in revolutionizing machine learning. By emulating the brain's parallel processing and energy-efficient nature, it could significantly enhance the capabilities of AI systems, enabling them to learn more quickly, adapt to new situations, and ultimately perform tasks that have thus far been challenging for traditional computers. Picture a bustling metropolis of information, where two distinct architectural styles vie for dominance: the towering skyscrapers of traditional computing and the intricate neural networks of neuromorphic computing. While both have their merits, they couldn't be more different in their approach to handling data. In the concrete jungle of traditional computing, data is processed in a sequential manner, akin to cars moving along a one-lane highway. Each task is broken down into a series of binary options, zeros and ones, that march through a linear path of processors, like an assembly line. It's efficient for certain tasks, but when it comes to mimicking the boundless intricacies of the human brain, traditional computing might feel a bit like trying to fit a round peg into a square hole. Enter neuromorphic computing, the avant-garde of AI architecture. Imagine a symphony of neurons firing off like fireworks, creating a dazzling dance of information exchange. At the heart of this revolution lies the spiking neural network, a key protagonist in our narrative. These networks are designed to mimic the behavior of real neurons, sending out discrete electrical pulses or spikes when they receive input. This creates a much more biologically plausible model for learning and computation. Think of it as the difference between a conventional light switch and a dimmer knob. Traditional computing relies on flipping the switch on or off, a binary action. In contrast, spiking neural networks use the rhythm of the spikes to convey not just whether something should happen, but also the intensity and timing of the event. This parallelism and subtlety in communication allow for more nuanced processing, as well as the ability to handle massive amounts of information simultaneously. As our digital cityscape evolves, the spiking neural networks of neuromorphic computing beckon with the promise of energy efficiency, lightning-fast learning, and the ability to tackle complex tasks that have eluded their traditional counterparts. The skyscrapers of binary might have served us well, but the neural networks of the future might just be the architectural marvels that bring true intelligence to our machines. Neuromorphic computing offers a remarkable solution to the energy inefficiencies of traditional computing in the realm of machine learning. Unlike the power-hungry transistors of conventional systems, neuromorphic architecture, particularly spiking neural networks, mimics the brain's efficient operation by using sporadic electrical pulses. This approach drastically reduces energy consumption, making it possible to perform complex computations while sipping a fraction of the power. This not only benefits the environment by lowering carbon footprints, but also extends the reach of AI to battery-powered devices, enabling real-time, energy-efficient applications in areas like remote sensing, mobile devices, and drones. Moreover, the reduced heat generation of neuromorphic systems simplifies integration into compact devices and data centers, enhancing hardware lifespan and reducing cooling requirements. In this symphony of innovation, neuromorphic computing's energy efficiency takes center stage, harmonizing the melody of computational power with environmental responsibility. Real-time processing benefits in applications like robotics and autonomous cars are paramount for ensuring rapid and accurate decision-making in dynamic environments. Neuromorphic computing, with its energy-efficient spiking neural networks, excels in these scenarios. These systems can process sensory data and make split-second decisions, such as detecting obstacles or adjusting steering and braking, with minimal delay. This capability enhances safety and responsiveness in robotics and self-driving cars, reducing the risk of accidents and enabling them to navigate complex, real-world situations effectively. Ultimately, neuromorphic computing's real-time processing prowess brings us closer to the dream of machines that can think and react as swiftly as humans, making our future roads and robotic assistants safer and more reliable. Neuromorphic computers harness the power of parallelism, a critical advantage over traditional computing. While traditional computers process data sequentially, one task at a time, neuromorphic systems, especially spiking neural networks, operate in parallel, allowing them to handle multiple tasks simultaneously. This parallelism mirrors the brain's natural ability to process vast amounts of information in parallel through interconnected neurons. This parallel processing is a game changer in machine learning and AI, enabling neuromorphic computers to excel in tasks that require massive data processing, such as image recognition, natural language understanding, and complex simulations. In contrast, traditional computers struggle to match the efficiency and speed of parallel processing, as they must queue tasks and execute them one by one. The advantage of parallelism in neuromorphic computing translates to faster and more efficient computation, making it ideal for tasks that involve large datasets and real-time decision-making, such as autonomous vehicles, scientific simulations, and advanced robotics. In essence, neuromorphic computing's parallelism opens doors to a new era of high-performance, data-intensive applications, setting it apart from the linear processing limitations of traditional computing. Neuromorphic computing excels at handling sparse data compared to traditional computing, thanks to its resemblance to the brain's operation. In neuromorphic systems, like spiking neural networks, data is processed in a spiking fashion, where neurons only activate when relevant information is present. This sparsity mimics how our brains work, firing neurons selectively in response to meaningful input. In contrast, traditional computing processes data in a dense, continuous manner, often requiring extensive computational resources to sift through irrelevant information. Sparse data can pose challenges for conventional systems, leading to inefficiencies, increased energy consumption, and slower processing times. The advantage of neuromorphic computing in sparse data handling is evident in applications such as natural language processing, where only a few words or phrases in a sentence carry crucial meaning. By mimicking the brain's selective activation, neuromorphic systems can process sparse data more efficiently, reducing computational overhead and enabling faster, more accurate results. However, challenges remain, such as designing efficient algorithms and hardware that fully harness the potential of sparsity in various real-world applications. Neuromorphic computing, with its unique blend of energy efficiency and parallel processing, holds immense promise across various applications. Let's explore its impact on three specific domains: edge computing, robotics and autonomous systems, and brain-machine interfaces. Neuromorphic computing is a game changer for Internet of Things devices, which often operate at the edge of networks. Its low power consumption and real-time processing capabilities make it ideal for analyzing sensor data, enabling more intelligent and responsive IoT applications from smart homes to industrial sensors. In healthcare, neuromorphic computing at the edge can process data from wearable health devices, allowing for continuous monitoring and early detection of anomalies. This can significantly improve patient care and reduce healthcare costs. Neuromorphic computing enhances the decision-making abilities of self-driving cars, enabling them to process sensor data, identify objects, and navigate complex environments in real time. This is crucial for improving road safety and advancing the development of autonomous vehicles. Robots equipped with neuromorphic systems can adapt to changing environments, learn from their surroundings, and perform tasks more efficiently. This is particularly valuable in fields like manufacturing, agriculture, and search and rescue. Neuromorphic computing can power advanced neural prosthetic devices that help individuals with paralysis regain mobility. By decoding neural signals and translating them into controlled commands, these brain-machine interfaces offer greater independence and quality of life. BMIs using neuromorphic technology can enhance human cognitive capabilities, assisting us with tasks like memory retention, language translation, or even real-time information retrieval by interfacing directly with the brain. In each of these applications, neuromorphic computing's energy efficiency, real-time processing, and ability to handle complex data patterns offer transformative potential. By bringing the power of brain-inspired computation to the edge, neuromorphic computing is paving the way for smarter, more efficient, and more responsive technologies that have the potential to reshape the way we interact with the world. While neuromorphic computing holds immense promise, it also faces several challenges and limitations. Neuromorphic computing hardware aims to mimic the intricate neural structures of the human brain, which is a highly complex endeavor. Designing and manufacturing such hardware requires cutting-edge technology and substantial resources. Achieving scalability while maintaining accuracy is an ongoing challenge, and it involves creating a vast network of artificial neurons and synapses that can process information in parallel, akin to the human brain. Neuromorphic systems demand novel approaches to programming and software development. Traditional programming languages and methods are often ill-suited to these architectures, which operate based on spiking neural networks and event-driven processing. Developing efficient software that can harness the full potential of neuromorphic hardware is a significant hurdle. Researchers and developers must establish new programming paradigms and tools to make the most of these systems. Integrating neuromorphic systems with existing computing infrastructure and software is not a seamless process. Compatibility issues can arise, leading to difficulties in data transfer and communication between neuromorphic and traditional computing systems. Achieving a smooth transition between these technologies remains a challenge, particularly in applications that require hybrid computing approaches. Neuromorphic computing is still a relatively young field, lacking established industry standards. The absence of such standards can hinder collaboration among researchers and developers. It also creates a fragmentation of efforts as different neuromorphic platforms emerge, making it challenging to achieve a unified ecosystem and ensuring compatibility across various hardware and software implementations. Neuromorphic systems excel at unsupervised learning and pattern recognition, akin to the brain's capabilities. However, they may face difficulties when dealing with structured tasks that involve rule-based reasoning. Striking the right balance between learning and reasoning capabilities is a complex research problem. Developing neuromorphic algorithms that can handle both structured and unstructured data effectively remains an active area of study, especially in applications where a blend of these capabilities is necessary. In conclusion, neuromorphic computing stands at the precipice of a transformative era in the world of technology and artificial intelligence. Its unique blend of energy efficiency, real-time processing, and the ability to mimic the human brain's intricate neural networks promises to revolutionize numerous domains, from edge computing to robotics and brain-machine interfaces. We've explored how neuromorphic computing can make IoT devices smarter, enhance the autonomy and safety of robotics and autonomous systems, and even open doors to incredible possibilities in brain-machine interfaces. Its benefits in energy efficiency, parallel processing, and handling sparse data are clear advantages over traditional computing, and they pave the way for more efficient, responsive, and sustainable technologies. Yet in the face of these promises, challenges persist, ranging from hardware complexity to the need for new programming paradigms. To fully unlock the potential of neuromorphic computing, we need a concerted effort in research and development. Collaboration among scientists, engineers, and organizations is crucial to address these challenges, establish industry standards, and propel the field forward. The call to action is clear. Invest in the future of neuromorphic computing. By doing so, we not only stand to create more intelligent and efficient technologies, but also unlock new frontiers in machine learning and artificial intelligence. The potential is immense, and the time to embrace this revolutionary field is now. As we navigate the complex challenges ahead, the rewards promise to be nothing short of groundbreaking, reshaping the way we interact with technology and advancing our understanding of the human brain itself. As always, thank you for taking the time to learn with me. If I missed anything or got anything wrong, please let me know, as I would love to learn more. If you liked what you heard, please consider subscribing. I appreciate the time that you've spent watching this video. No matter who you are, you only get 24 hours in a day. Thank you for spending a portion of that with me. See you next time.